to artificial intelligence. Deep learning, anyway, is not just a subset of AI, but it is a very important one, because you can see nowadays deep learning used for a wide number of very incredible tasks. And even if cannot yet manage everything that we expect it to do, it's really fantastic. And deep neural networks are the algorithm behind deep learning. Why is it relevant, deep learning? Yes, it can achieve a lot of tasks because it is associated with the idea of software 2.0, as Andrea Carpati explained from Tesla. It's a new paradigm where you actually don't need to program anymore your computer, but actually you just have it to learn from your data. And this brought about very incredible advances in AI, such as self-driving cars, which are actually quite a reality in testing, deep learning in healthcare, deep learning in search engines, which actually we experience every day when we use Google, voice search, voice activated assistants, and so on. But if you are a practitioner, you may have noticed that deep learning is mostly related to problems with data from images and speech and text. But most of your data, the data you work every day, is actually not of that kind. It derives from databases, which are an innovation from the 60s of the previous century, and your data is split into tables. And such data is often very messy and very complicated to be dealt with. So if you want to analyze and produce predictive models using tabular data, you actually have a few challenges that are unique to deep learning. And actually, you have mixed features data types, which are quite a problem. And if you deal with, for example, categorical data with binary encoding, you have sparse data, which is not the best for this kind of algorithm because it cannot perfectly fit it. And sometimes you have even less data than in image recognition problems, because even if your data is a lot, you will discover that the most common information is the null field, or for your specific very important problem, you don't have the so many data as we expected. Moreover, there are no best practices. There are no state-of-the-art models, pre-trained ones that you can leverage for your tabular data problem. And even when you manage to create something with deep learning, there's a suspect for all the people sharing with your project that you are using an algorithm which is less interpretable, which is actually a little bit complicated and very difficult to explain. And moreover, in the field of machine learning algorithms, you have a problem that sometimes just using a gradient boosting, which is a completely different kind of algorithm, you can get better results. But don't get discouraged. There are many challenges when you try to apply deep learning to tabular data, but so are the opportunities. Andrew Yang recently talked about this challenge as the new frontier for deep learning. So what can you do actually? It takes some effort, but you can manage, because you don't need, first of all, to reinvent the wheel. You can use TensorFlow and in particular Keras, scikit-learn, and pandas for your projects. You can process and pipeline input data, and so deal with its variety according to its type. And this is actually something that can be done for all the kind of data that you can deal with. And you also create a suitable neural architecture by experimenting and by keeping into account the number of examples that you have. You can use regularization to face the problems of over complexity of your network. And you can, as in other machine learning algorithms, encode all your prior knowledge about the problem. So you can do naturally feature engineering. In the end, you can test and tune your network using cross-validation, as you do with other machine learning algorithms, and you can get very good results. But let's talk now about the three challenges that I mentioned you before. First of all, data preparation. You can use the right tools. I prefer TensorFlow with Keras, and I prefer to mix them with scikit-learn and pandas. Why? TensorFlow is a high-level API. It's robust and effective, and it's production-ready. Scikit-learn and pandas have fit transform methods, have a host of classes for data processing, and also they offer cross-validation. So if you want to integrate everything, you can just think of this kind of framework where you have a data generator. Inside the data generator, you can put a tabular processor, which is a piece of code which takes different pipelines, each one pointing out to a different part of your dataset, characterized by the same kind of features. For example, you can have a pipeline for numeric data, a pipeline for dates, a pipeline for categorical data. After your data is inside a data generator, you can, of course, put it into a TF data dataset, which will help you cache and further more transform your data, or you can just directly feed it into your Keras model. You can find an example of this kind of approach if you just take a look at the GitHub account that I actually prepared. For example, when you deal with numeric variables, you can create pipelines excluding in sequence low variance variables, deal with missing values, strive to make your data more Gaussian-like, so do some transformation, catch outliers and just crop them, and normalization. For instance, it's something that you shouldn't ignore, that if the data you take into your deep neural network is transformed in the way that is the most normal as possible, it will bring you better results. And for example, you will see the quantile transformer from the scikit-learn package that can transform even very rough distribution into normalized data. Also, this can be dealt very easily using pandas, so they can be transformed into, for example, cyclic continuous variables. Even here is very easy to fit everything into a pipeline. You just transform your data, no matter what's its format, into the datetime64 format, and then you can transform it using cosine transformation, sine and cosine transformation. Also, when you have a low cardinality, for example, categorical variables, you can use one-hot encode, and here you have again your one-hot encoder from scikit-learn, and then using, for example, the same strategy, you can also deal with categorical ordinal variables. Anyway, Keras is becoming more independent, so we can expect in the future even not to use scikit-learn for dealing with such pipelines. For example, recently, Francois Chelier mentioned about a recent development, which is the Keras Preprocessing Layers, which are a set of layers that can help you deal with most of the operation that I mentioned before. So it can be found at this GitHub address, and the Keras Preprocessing Layers allows you to actually build layers that input your data in a Keras native way. So it's like another layer of your deep neural network. And models built with such preprocessing layers are truly end-to-end. So we have characteristics of model portability and server reliability. You can easily just export your model and everyone can use it without having to figure out how to best deal with data preparation. And the same is at serving level, because you just export to, for example, a server, your model, and it can already be production ready, serving all the inquiries. Also, you can leverage simple optimization using, of course, the TF data modules and the TF transform. And in this way, you take away all the preprocessing from the critical path of your model deployment. We just have a very quick look about what these new preprocessing layers offer. You have a function for feature transformation, for example, normalization, which is quite important for your neural network because it has actually to receive data which is constrained in certain bound numeric limits. You can have a string lookup, so you can transform strings, categorical values, into integers, which is actually label encoding in scikit-learn. And you have also integer lookup. So even if you have numbers which are not continuous, you can transform them into continuous numeric labels, which is quite important for inputting in your neural network. You also have categorical encoding. So you have categorical encoding layers, which can transform all your categories. So variables which are inherently qualitative, for example, color could be red, green, and blue, could be immediately transformed into one-hot encoded binarized variables. You also have a hashing layer. If you don't have security and certainty about what kind of categorical inputs you will receive, so hashing layer will just force them into a preordinate binary set of encoding variables, and then you have discretization layer, which can help you transform numerical variables into categorical ones, so deal with numerical and categorical in the same way. And finally, you have a feature engineering function, which is the category crossing layer, which performs combination of variables, so interactions, which can be quite important. And later we discover why, because if you have experience with deep neural networks, you know that actually when you input variables, they are actually mixed implicitly by themselves inside the different dense layers. But this is actually not enough. I concluded this part just mentioning two ways for dealing with preprocessing layers. The first one is use them as a part of your model, which is the best way because all your data processing will be dealt with GPU or TPU, and also you assure model portability. But in some cases, you can just apply them to TF data dataset. So you can just separate them from the model, because in this case, you can also work out your model using CPU, which is quite convenient, for example, when you're dealing with many images and the processing of images is quite heavy. So in order not to have latency when you are just picking up the images from your disk, your storage disk, you can use multi-core CPU to just process them in parallel. And so I have always a continuous uninterrupted feed to your deep neural network. We arrive now at the second challenge, which is about categorical data. I mentioned that actually you can deal with categorical data by binarizing them. So you use the one-hot encoder and you transform each variable into a series of 0 and 1s when that particular level of the variable is appearing. But this doesn't work when you have high cardinality variables. What does it mean? When you have a categorical variable which has a very high number of unique values. For example, you have a variable depicting geographical areas, geographical places, or for example, ID numbers or other characteristics, such as, for example, in CTR, you have click-through rate modeling. You have, for example, this site where the advertising appeared, and there are many sites. So in order to deal with that, you really cannot use just binarization of the levels of your variables, because deep neural network doesn't work quite well with very sparse inputs. It really doesn't backpropagate, so it doesn't adjust correctly its weights in order to provide you the best possible forecasting. So you need to deal with them in another way, and the best way is using encoding layers, as described in this paper. Let's take a look at how it works. An embedding layers is just a matrix of weights. It converts the input size, or your input, which usually is a number dictionary, to a lower dimension output, so the embedding size. It is a weighted linear combination, so the weights are optimized to predict, and it is quite simple to understand, because actually in the next two slides we are going in deep with layer, and the resulting embedding is exportable and reusable. So for example, if you have a textual label like AD8080, which is one of a number of variables, and in this case, just to make it simple and just say that you have just 12 labels, but normally you can have even millions of these. And it has label encoding too. So this is by the embedding layer, just transformed in a smart way into a one autoencoding vector. So you can imagine a sequence of zeros where only one is breaking the sequence, where actually that particular level, in this case, is level 2, number 2, is appearing. And this enter the weights matrix, which is size. In this case, since your input is 12 by 4, because we expect 4 as an output, and then you have the densification of your input. So the label encoding is transformed into one autoencoding and then transformed into 4, in this case, output variables. And then after that, you can pass them to all the Fourier processing in the deep neural network. The weight matrix is actually adjusted by backpropagation because initially randomized, with an initial random values, it just gets adjusted by iteration and iteration. And here you can see more in detail how it works. It's very important because it's the core technique you will use when dealing with categorical data and tabular data problems with deep learning. So you see, you actually, here we receive a label 2. It is implicitly, and I'm going to explain what does it mean, implicitly transform into one hot encoding series of binary variables, and then this is multiplied by the embedding matrix. After that, your output could be, for example, regularized by a spatial dropout to one dimension, and it results in 4 variables. But in this case, we decided for 4. You can decide for any number of output variables because it's kind of factorization. You decide the dimension that you want to output, and this dimension can be actually related and understood in analogies with latent variables. And I mentioned before that your label is implicitly transformed into one autoencoding, because if you see exactly, your result is the row corresponding to the label. So actually, there are no matrix multiplication when you just apply the embedding layer in your deep neural network, but it's just a lookup. So it's very efficient, very fast. But this is an incredibly powerful technique. Just think that companies like Pinterest and Instacart created their embedding layers, and they reuse them for many, many problems, because if you create them on the variables you need to work on, in case of Pinterest, for example, the interest expressed by the various pinboards in Instacart are actually the expenses of their customers. You can very easily transform them into something usable by any kind of machine learning algorithm. As I said, it's just a lookup. And in Keras, this is very easy to export because you just get the weights and you can save them. And now we are ready for the third challenge, which is the neuron architecture. In this last part, I want to share my experience about the next step after you successfully dealt with input pipeline in deep neural networks. So you just can basically deal separately with the different kinds of inputs. And you can deal with what is categorical using the embedded layers, which are a very powerful solution. But architecture, what can we do? Personally, I have an experience in multivariate statistics. So when I actually studied neural network the first time, quite long time ago, the input was that they are another parameterized method. So they are very prone to overfitting, and they actually don't work well when you have too many hidden layers, too many connections. But by practicing it, by using it for real world problems, I slowly realized that actually the power of deep learning is when you go beyond, actually with over-parameterization, the limits of your dataset. An example that our researchers discovered, in this case we're talking about OpenAI, is the deep double descent, which actually is a little bit counterintuitive in respect of what you may learn in classical machine learning. In classical machine learning, you learn that you have a trade-off between bias and variance. So when you increase the representation capacity of your algorithm, machine learning algorithm, you actually incur higher variance in your prediction. So you have more overfitting, more errors. Well, of course, you can learn more than data. There's this trade-off which can stop you from learning at a certain point. Actually, in deep learning, many researchers and practitioners discover that the more you increase your model, the more power you give it by enhancing the layers, using more nodes, using more processing inside the neural network, the better results you get. How is it possible? Actually, this is related to the fact that if you just fit your problem, you won't get good results because you overfit. But if you overfit, you can get better, especially if you regularize. Let's have a look at this tweet from Francois Fleuret from Geneva University. Actually tested, for example, a very simple problem with just a few points and polynomial fitting. And the result is quite interesting. Actually uses some kind of regularization at a certain point. But as you fit, for example, a series of training samples and you use low-level degrees in respect of its complexity, so you are putting more bias, you have some reasonable fitting, which actually can get a rock when you overcome a certain number of degrees in your polynomial fitting spline. So for example, you see in the lower left part at degree 7, you don't have a very good result. But the incredible fact is that if you increase your degrees, so if you just make more flexible your fitting, you actually can get a very good result. And you can see it in the lower part of the right side. And this happens exactly with neural networks. And so you can see here the result of experiment with professor. And this takes us to core about this presentation, which is about categorical feature encoding challenge, which is a Kaggle challenge. Actually took place a few months ago. You may have gone unnoticed it because it wasn't awarding any kind of prize or ranking, but it was quite interesting. It was the second of its kind. There has been a cut in the dot #1 before. It hadn't been so interesting, the first one, but this time features were not independent as in the first challenge. And the problem was more multivariate, more similar to real world problems. You had a dataset with 600,000 examples, so you didn't have a problem of few data, but it contained only categorical features, included binary features, low and high cardinality luminal features, high cardinality ordinal ones, and even 2 potential acyclic features related to time. And I took myself the challenge, the competition, and as others, I discovered by specialized approaches on categorical data, such as, for example, CatBoost, the gradient boosting algorithm specialized on categorical data, and of course, deep neural network with embeddings perform very, very well. And you can actually also blend or stack such solution together. So, for example, I prepared 2, and not being the only one, 2 kernels just showing these approaches, but such approaches were not enough because top solutions were a little bit different. So we have 2 solutions, one at first place and one at second place, that mentioned that yes, they use ensembles to win, but the key of their success was the presence of extreme deep factorization machine, and especially the use of the thin layers, so the compressed interaction network. What are we talking about? First of all, a brief mention about factorization machines. Factorization machines are something that is not so common to be found in Kaggle competition because it's not part of a scikit-learn stack. But who could use it in different in previous competition really got very good results. How does we work? We work in the principle that by using polynomial expansion, you can get all the interaction you need in order to fit in the best way a problem. So they just use a trick in order to create all possible interaction without actually creating them. So they are very powerful. You just tell them how much you want to have your variables interact. For example, you say, I want to arrive, for example, to interaction of a 10th grade. So you can imagine 10th variables interacting together and but one new feature. And factorization machine, we just project the input into actually a lower dimensionality space and just do the interaction there. It's kind of something similar to singular value decomposition. So you create latent vectors which can synthesize and express the richness of your input data, and you work with them, and they're very successful. So it was not a surprise that the very similar approach can work with deep learning. And the first trial was with white and deep learning, which is a network of a few years ago, where this one was developed by Google. And you have your network split into two parts. One part is just taking the information directly from the input data and putting it in the, like a linear combination in your answer. Another part using embedding. And by embeddings, just projecting then the information into a series of dense layers. In this way, you actually can have both the representative power of deep learning and both actually the general power of machine learning all put together. But this is not actually the perfect situation, because as we have seen in factorization machines, you actually create all possible interactions, and we are implicit one. We are not related to the interaction that maybe can bring the best result. So extreme deep factorization machines is kind of advancement of this approach, because the inputs, which are categorical, so also numerical, can get into categorical by discretization, are embedded, and they take three different ways. One way is the linear one, so they are just linearly combined. One way they are dealt as in the white and deep network, so with layers of plain dense layers. And then you have this compressed interaction network, which is something very clever as architecture, which allows actually to create all possible interaction for your data and just keep the ones that care for your problem. So here you have some figures from the paper, and basically you have just to point out, because we don't have so much time, to the fact that the output that you can see on the figure on the left, which is just taken from a series of feature maps, is dealt like a recurrent neural network, because your input is actually related each time to the initial input and transformed into these feature layers, which are stacked together. So the later feature layers are actually a multiplication of a previous one. This helps the network to control the level of interaction. So you can just say, I want to arrive to, for example, the 10th grade of interaction, and the network will be just set to 10 feature layers, and each one will provide a certain level of interaction. Moreover, the interactions are actually selected, because at the base, and you can see in the second and third image going to the right, are actually selected by a way very similar to convolutional neural networks. So you have a convolution that just picks up by reducing, this is the sense of the compression, the tensor of data into the feature map. And by doing so, it just retains the critical information. You have two fantastic implementations, which I actually tried and can make like a breeze, easy like a breeze to use this technology. Deep tables, and you can find here the address, and deep CTR. CTR is click-through rate, because actually these kind of models are particularly performant in a recommendation and click-through rate problems, since they deal with very sparse data. And so also the time is running away. We are almost at the conclusion. So I just wrap up. Deep neural networks for tabular data are, in my opinion, an alternative solution for modeling a response given tabular data. And in my experience, are particularly performant when you create alternative models with machine learning, such as gradient boosting. Neural networks are kind of interpolating approach to your problem. If you just mix them, for example, by a blending or a stacking with different approaches, such as gradient boosting, which is a more analogy approach, you can get the best results and really performing solution. But neural networks, as we have seen, require Docker architecture and well-crafted pipelines. Now they are becoming easier to build because we have specialized layers and packages as the one I presented. And I just remind to you that it's very important to become proficient with entity embeddings, because they are the core tool for categorical data in deep neural networks. And as a final takeaway, never overlook a Kaggle competition, because especially the Kaggle competition, which don't bring ranking and medals, are the most interesting ones. People share more, and something very interesting like the extreme deep factorization machine can come up for you. So I conclude, I thank you, and just return the word to our moderator for all the questions you have. Thank you.
Thank you, Luca. This was very, very insightful. We have some questions from the attendees.
Yes, please.
So the first one is from Vikram. Vikram
Yes.
is asking, can a node in a network itself be a multi-dimensional array, or does it has to be a scalar value only?
So multidimensional array means, for example, a three-dimensional. Yes, actually, you can have this kind of input. You can deal with it in different ways. Recently, there has been a competition in Kaggle just dealing with a similar problem, which was an healthcare problem. And basically, if you have different dimensions, you can just deal with slices of them and then process each slice with a neural network, and then take all the results from the slice, for example, in a straight stacking regime, into another neural network, for example, having recurrent neural network layers, which can help you. Or you can just deal directly with them, for example, using convolution, because you just don't have convolution, which has bidimensional, but also three-dimensional, for example. So actually it's possible, but it means that if you are dealing with tabular data, you have this problem. You're probably dealing with time. So I think there is not one standard solution.
Okay, our next question is from Anshu Kumar. Anshu, we are allowing you to please speak up your question yourself.
Hi.
His question is, can we apply transfer learning for tabular data, interdomain, intradomain?
As I mentioned, we don't have state of the art, and myself sometimes I puzzle why we still don't have it for tabular data. Probably because tabular data has a very huge variety of different, specimens of data. So it's not like images, it's not like text. Basically, the embedding layers, as I mentioned, they can be exported. So you can use embedding layers as pre-trained for when you are using deep neural networks for tabular data. Basically, there are no free ones around, but if you have, like, for example, Pinterest or Instagram, problems related to tabular data, you can create an embedding from one problem. And when you have another problem, using the same variables, you can use that exact same embedding. So using pre-training effectively. Unfortunately, we are still far from having a network that can solve all the problems. But for your specific field, you can create your pre-trained ones. But it's up to you, unfortunately.
Okay, the next question is by Rajni.
Yes?
Hello, Mr. Luca. Good afternoon.
Hello.
Yeah, my question is for using deep learning for tabular data, what is the minimum size limitation? Usually, because the size of the tabular data cannot be compared with the size of the image data, or that is usually used for deep learning. So, does it have any minimum size limitation that we have to keep in context or mind to use this?
Yes, very good question. Thank you. I would just remark that I cannot say you have a minimum data size, because myself, I have been amazed at using very small sizes, even in comparison with standard machine learning problems, working very well with neural networks. As I mentioned, even if you offer in this kind of problem you have with few data are over parameterized neural network, you can still get very good results. So recently, I cannot go into details, but I have a very small data set of a few thousand examples. Actually, my networks have 24 million parameters. No memorization happened, and the network provided state-of-the-art prediction. I couldn't get anything better using gradient boosting. But it's very important when you face these problems, you have few data and you create a very large network that you regularize. Regularization is the secret. So please use batch normalization, use most important dropout as much as possible. And also if it works well for your problem, just add to your dense layers L1, L2, or together regularization, because actually you can just, twinkle dense layers to have this kind of regularization. Regularization is very important when you have more parameters than examples. And don't have fear to try these methods, even if you have very few examples.
Thank you, Mr. Luca.
You're welcome.
Thank you, Luca. That's about it from our attendees, and it was a very insightful session. We are glad that you could make it to the conference. I would urge you to be there at the conference at our lounge. If anybody would want to connect with you one-on-one, they would love to do that.
I will be glad to. Thank you everybody for attending this session, and I will try to connect as much as possible today. Unfortunately, now I'm starting work in a few minutes because here in Italy we are a few hours earlier, but I will keep contact with all of you, and thank you again for attending, indeed.
Thank you.